Okay, so in this lesson, we're going to go over and talk about what a series is, which you guys saw a bit of in Math 3. We're just going to review that. We're going to talk about geometric series, which is also a review, and then the nth term test. Before we start, let's look at, just remind you what the definition of a factorial is. For example, if I have 5 factorial, what that really means is to go 5 times 4 times 3 times 2 times 1, right? This is n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. So that example 1 says simplify. You have n plus 2 factorial over n factorial. So if you think of it this way, now if we go, the top one is n plus 2. If I go down 1, it'd be n plus 1. Go down 1 more, it would be n. And I'm going to stop there because I'd keep going, right? Go down n, n minus 1, n minus 2. But I don't have to go any further because now on the bottom, I'm also going to have an n times n minus 1 times n minus 2. So what ends up happening, really, is those two just reduce or cancel out. Real quick example is if I had 5 factorial over 3 factorial. So what really happens there, right, is we end up getting 5 times 4, and I can stop right there because down here, right, this is end up being 5 times 4 times 3 times 2 times 1, 3 times 2 times 1, and those factors just reduce. So when you get to this point, we can just reduce those, just like over here, that n factorial and that n factorial reduce there. Okay, we'll use factorials a bit on this assignment. Okay, so we're going to talk about what a series is. So a series is really simply put is just a sum of numbers. And you guys remember this sigma notation? You saw it last year. It says an infinite series can be represented as, okay, we got n equals 1, right? And you have the summation notation or sigma notation. And infinity is where you stop. So in this case, a series goes on forever, right? So let's take A1 plus A2 plus A3 and goes on infinitely. So this example 2 says write out the first 5 terms of the sequence. So if I plug in 1, I would get 1 over 2. If I plug in 2, I'd get 2 over 3. Plug in 3, I get 3 over 4. I plug in 4. If I plug in 5, right? And that's going to keep going. It's going to follow that pattern, but it asks us to write the first 5 terms, and that's what we've done. Okay, so if you look at example 3 and 4, we're just working backwards. It wants me to write an expression for the nth term of the following sequences. So I want to come up with, like, the first term I get 1, the first term of this series. The second term of the series I get a 4th, a 9th, a 16th, a 25th. I want to come up with an expression that represents, the nth term. So I could find the 10th term or the 20th term or the 100th term. So if you look at what's happening here, if you notice if you write that as 1 over 1, if you notice in the denominator, the first term I get 1, second term I get 4, third term I get 9, fourth term I get 16, fifth term I get 25. So really we're just squaring whatever the term is. So if I want to find the nth term, I'm going to go 1 over n squared. So see if that works, right? If I pick the third term, I'd plug 3 in, I would get a 9th. If I pick the fifth term, I'd plug 5 in, I'd get 1/25th. Okay, let's look at this next one. So you'll notice that the 3 on the top is staying the same. But I've got to come up with some expression. The first term I get 1, second term I get 2, third term I get 6, fourth term I get 4, or 24, sorry. Fifth term I get 120. So this one's a little tricky, at least I think it's tricky. But if you notice in the first term, to get from the first to the second, we're timesing by 2, then we're timesing by 3, and then we're timesing by 4. So you can actually, if you look at this, this is actually 1 factorial. This is 2 factorial. Remember, 2 factorial is 2 times 1. This is 3 factorial, right? 3 times 2 times 1. This one is 4 factorial. 4 times 3 times 2 times 1. And then this one is 5 factorial. So that's a little bit tricky, but our expression for the nth term is actually going to be 3 over n factorial. Okay, is what that comes out. Okay, that's important. Like that step right there is important because when we want to write the expression using sigma notation, we have to come up with an expression for the nth term. And so I'll show you kind of what that looks like down below. Okay, so if you look at this, it says write an expression for the following series using sigma notation. Just like we talked about, right? That sigma notation is using, right? We're using that right there. Okay, so let's see if we can come up with this. So we're going to, terrible at drawing sigmas. Okay, and we're going to start at n equals 1. You don't have to start at n equals 1, but you'll see that a lot. And we're going to go to infinity. The reason we're going to infinity, right, we got the dot, dot, dot. This is an infinite series. Okay, then I just need to come up with an expression that represents the nth term, similar to what we did on number 3 and number 4. And if you notice, both the top and the bottom, like on 3 and 4, the numerator was staying the same. It was only the denominator that was changing. On this one, both the numerator and the denominator is changing. So we've got to come up with an expression that's going to give us both of those. The bottom one's a little bit easier. It's just going up by 2 each time. That means it's a linear pattern, right? It's going from 1 to 3 to 5 to 7. So because it's going up by 2, it's going to be 2n. And then I got to figure out what the starting, well, when I plug 1 in, right? When I plug 1 into 2 and I get 2, it needs to come out to be 1. So I'm just going to subtract 1 off there. We'll see if it works. If I plug 1 in, I get 2 times 1 is 2, minus 1 is 1. I plug 2 in, 2 times 2 is 4, 4 minus 1 is 3. Plug 3 in, I get 5. So I think we're good there. Up on top, we got to come up with an expression that represents that. If you look at it, it's also going up by 2. Okay, so I'm going to do a 2n. If I plug in 1, I already get 2. If I plug in 2, I get 4. Plug in 3, I get 6. Plug in 4, I get 8. So I think we're good. So all you're doing when you're writing an infinite series like this using sigma notation is, right, we're using our sigma notation. This part here is just a formula or an equation that gives you the nth term. Okay, let's look at this next one. This one's a little bit tricky. You'll notice that it's alternating. I've got positive 2, negative 6, positive 18, negative 54, positive 62. So we'll have to figure out a way to deal with that. Let's see if we can come up with a formula here. So we're going to go. If you notice, you're really timesing by 3 every time, right? 2 to negative, actually by negative 3, excuse me. 2 times negative 3 is negative 6. Negative 6 times 3 is negative 3 is positive 18. 18 times negative 3 is negative 54. So I'm going to put this, I'm timesing by negative 3 each time. Okay. And then I need to come up with that first term. Now this can be a little bit tricky. If I put a 0 up here, I'd get negative 3 to the first power, which is, sorry, negative 3 to the 0 power, which is 1. Then I could times by 2. So that works for the first term, right? Negative 3 to the 0 is 1, times 2 is 2. If I plug 1 in, negative 3 to the first power is negative 3, times 2 is negative 6. If I plug 2 in, negative 3 squared is 9. 9 times 2 is 18. So in this case, I want my n to start with 0 instead of start with 1. And then we're going to go to infinity. This is not the only formula you can come up with. Also, you can actually make it so n equals 1. Like there's different answers here that would work. Just to save time, I'm not going to get into that. But just be aware that there are different answers you can different formulas you can come up with, and you can adjust. A lot of times this n equals 0 can be adjusted, and you can start with 1 also, and you'll see that as we go through some of these examples. All right, 7 says, what happens if we add more and more terms of a like series? Okay, so just think about what's happening with this one. If I just add the first two together, right, 1 plus, well, if I just take the first term, and it's just going to be 1. If I add the first 2, it's going to be 4. If I add the first 3, 1 plus 3 plus 5, it's going to be 9. If I add the first 4, 1 plus 3 plus 5 plus 7, that's going to be 16. If I went out one more, right, the next number would be we're going up by 2 each time, so that'd be 9. So 1 plus 3 plus 5 end up being 25. And we could keep going. That's what it's talking about, to show a sequence of partial sums. I just took the first term, then I added the first 2, then I added the first 3, then I added the first 4. And we're kind of looking for patterns on what's happening as we add those together. So it says this sequence of partial terms is approaching infinity. And what that means is it's just going to keep going up, right? My next one's going to be 36. And there's a definite pattern to it. But it's approaching infinity. That sum is getting larger and larger. Okay, when that happens, we call it a divergent series. So think of the word divergent. Okay, we're going to talk about convergent in a second. Okay, divergent just means that you're going away from something, right? You're diverging. Whereas converge means you're getting closer to something. So kind of keep that in mind as we go through and look at these next examples. So example 8 says, what happens if we add more and more terms to this one? So let's actually write out our series. If I plug 1 in, that'd be 3/10. If I plug 2 in, that'd be 3/100. If I plug 4 in, it'd be 3/1000. Okay, we can keep going. So think about what's happening with this one, and this is kind of weird. Sometimes this blows our minds because this series is infinite. We're going to keep adding more and more numbers, but as we do, these sums actually converge on an actual number. Probably the best way to illustrate this is almost to think of this as a decimal. 3/10 is 0.3. If I add that to 3/100, that's 0.03. And 3/1000 is 0.003. Anyway, as I add this up, I'm really just going to come out to be 0.3333 ... That's what's going to happen as I keep going out. Well, that's really just equal to what? To a third, isn't it? So again, this is hard sometimes for us to visualize or to understand. But you can see that as I add up these sums, it's converging on 0.3 repeating, or 1/3. So even though it's an infinite series, we're never stop adding numbers to it. It's converging on a certain number, which is a third. Okay, so this is what's called a convergent geometric series. Okay, so let's just review really quick what a geometric series is. Right, it says if consecutive terms in a series have a common ratio, R. So if you have that common ratio, we call it a geometric series. You guys have seen these. You see these in Math 1 and Math 3, and I think you'll recognize it when you see it. So here's an example. If I have A times R to the n, right, I start out with A times R to the 0 plus A times R to the first plus A times R to the second. All we're doing to going from this term to this term to this term is we're just timesing by R all the way across. So that's what it's talking about, is that common ratio R. You're timesing by that same number each time as you go. So if a geometric series converges, you can find the sum. Like that's what it's saying down here, right? If a geometric series converges, it's possible to find the sum, even if it has infinite terms. So here's a quick little proof on how this is a way you can actually find the sum of infinite geometric series that converge. So up here, right, this is kind of what we're just talking about. And let S equals A plus AR squared plus AR cubed, just timesing by R each time. So if I times by r, I end up with AR plus AR squared plus AR cubed, dot, dot, dot. Okay, and then it says we want to subtract those two. So if I subtract those two, right, these are just going to cancel out. I'm just going to end up with A right here. So that's equal to A. All right, S represents the sum. Okay, and then if I divide by 1 minus, divide by 1 minus R, I end up with this formula. So the formula is this. If you're finding the sum, again, this only works for converging geometric series. So if it's converging geometric series, I just take the first term A, right? A is your first term, and I divide it by 1 minus the common ratio that you're finding there. So make sure you label this. This is really important, is A is the first term, and R is the common ratio. Okay? So you have to know those two things. If you know those two things, then you can find the sum, right, of this infinite geometric series. Now, just a side note on this. This proof is only valid if the series converges. And when you talk about subtraction, it's defined for finite numbers also. Okay, so this is not going to work for subtraction. So this is the formula we just talked about, right? So if I want to find the sum of an infinite geometric series, as long as it converges, I just take the first term A and I divide it by 1 minus R. Okay, to tell if it converges then, this is important to know, right? Because this formula only works if it converges. You know, if it diverges, then the sum's going to be infinite. You can't find it. It's just going to keep getting bigger and bigger. So the way we tell is this, right? The geometric test for a geometric series, okay, and geometric series can always be written this way, is you look at the common ratio. Okay, if it's greater, if the absolute value is greater, whoops, didn't mean to scribble that out, sorry. Meant to highlight it. If the common ratio, the absolute value of the common ratio is greater than 1, it diverges. If the common ratio is less than 1, the absolute value of it, then it converges. Okay, so go through and look at that. Okay, so let's look at some examples. This one says determine if the series converges or diverges. If possible, find the sum of the series. All right, so we're looking at this one. This one's a little bit tricky because it's hard to see what the common ratio is, but you could rewrite this way. This is the same. Whoops, sorry about that. You could write this way. Really bad sigma. This is the same thing as a half to the nth times 3, or 3 times a half to the nth. So if you look at what the common ratio is, and if you aren't sure, you could plug in a couple numbers, right? If I plugged in 0, I get 3. If I plug in 1, I get 3 over 2. If I plug in 2, I get 3 over 4. So you can see what's happening. You're timesing by a half each time. Well, the absolute value of R, the common ratio, is a half, and that's less than 1. So I come up here. That means it converges. That means we can find the sum. Okay, so the sum is equal to my first term, which is 3, divided by 1 minus R, which is a half. Okay, so that ends up being 3 over a half, okay, which comes out to be 6. So if I take the sum of that infinite series, then we have to add all those up. All right, let's look at this next example right here. Okay, this one, right, if I do the first term, this one would be, if I put in 0, this would be 1. If I plug in 1, it'd be 3 halves. If I plug in 2, it'd be 9 fourths. So when you see what's happening each time is you're timesing by 3 halves. So R is equal to 3 halves. So the absolute value of R is still 3 halves. That is greater than or equal to 1. Okay, so this one diverges. Okay, and we know that because of this geometric series test. Okay, let's look at this next one. So we're checking, and this time we're timesing by a negative 1/2 each time. So the absolute value of R would equal a positive 1/2, which is less than 1. And what that means is that this series, right, is right up here, it converges. That means we can find a sum. Okay, my first term, if I plug in 1, I get 4 times negative 1/2 to the first power, which is negative 1/2. We times those, I get negative 2. So negative 2 is the first term. So the sum is equal to negative 2 divided by 1 minus, and we take what r is, which is a negative 1/2. Okay, so we end up with negative 2 over 3/2. Okay, so we times by 2/3, and we end up with negative 4/3. Okay, that is the sum of that infinite series. So this is kind of a cool question. It says, write the fraction form of a repeating decimal of 0.08 using a geometric series. Okay, so if you think about this, if I take 0.08 repeating, that means 0.08 plus 0.0008 plus this is the same as 0.080808. We can write it out this way. 0.00008. Hard to keep track of those zeros. Anyway, it just keeps going. So in this case, if I think of it as an infinite series, that first term that's the first term right there, is 0.08. Okay. And then when I'm timesing by each time, if I think of those as fractions, maybe that would be easier. If I think of those as fractions, this would be 8 over 100. Okay, this would be 8 over 10,000. This would be 8 over 1,000,000. So my first term is A equals 8 over 100. And then what I'm timesing by each time is 1 over 100. Okay, so we're going to plug this in here. So the sum is equal to my first term, 8 over 100, over 1 minus my second term, which is 1 over 100. So we end up with 8 over 100 times by, this would be 99 over 100. So if I times by the reciprocal, we end up with that. Those cancel out. So that is 0.08 repeating written as a fraction. So kind of cool. You can use this. You can find the sum in order to switch it to be a fraction, which I think is awesome. Okay, look at 13 for a second. It says we got this series here. It says it does not converge. Like if you check those numbers really quick, if I plug 1 in, we get 2, and then I plug 2 in, we get 3/2. If I plug 3 in, I get 1 1/3, which is 4/3. You could plug 5 in, or 4 in, excuse me, and you get 5/4. So as you go, those numbers are getting smaller, but this is really important. It does not converge. Right? If you start adding up these partial sums, if I add up the first two, the first one is 2. If I add up the first two, I would get 3.5. I add up the second two, or the first 3, excuse me, it comes out to be 4.83. If I add up the first 4, it comes out to be, I didn't mean to put a plus there, sorry. I'm just adding up these partial sums. If I add up the first 4 terms, you can grab a calculator and plug that in, it comes out to be 6.083. So even though each term is getting smaller, when I add up the sum of the terms, it is not converging. Right? So a series cannot converge unless it approaches 0. So here's how you test. This is the nth term test for convergence. Okay, what I'm going to do, really simple, is I take the formula for the nth term and I find the limit as n approaches infinity. And that if it goes to 0, okay, if it doesn't go to 0, that means it diverges. If it does go to 0, it's inconclusive, but that means it could converge. Okay, so let's try this one right here. This is what it means. I want to take this, and I'm going to find the limit sorry, my brain went dead there for a second. As n approaches infinity of that, which is n factorial over 2n factorial plus 1, and we want to show that it diverges. So I'm going to simplify that bottom part. Just think about what happens here. The plus 1 is insignificant. because as n gets really big, this part and this part's going to overtake everything. So what's going to happen, right, is they're essentially going to cancel each other out, and I just take the leading terms. So that comes out to be a half. Well, that does not equal 0. So if I come up here, all this says, if it doesn't equal 0, that automatically means that it diverges. Okay, so we've just shown that it diverges. So this is the nth term for divergence. Now, if it does go to 0, then it could converge, although it's not conclusive. Like, we can't tell for sure. So that's a little bit tricky. Okay, I think that's everything you need to know for that first section.